This workshop, when I looked at the website, seemed to me to have at its core the question, what is information? To head toward an answer to that question, I'd like to tweak the question a little and split it into two. What can we get from information? How can it be useful? And from what can we get information? I'm going to tweak those questions again, and in the context of small-scale thermodynamics. Finally, there's another question hidden on the slide, namely, is small-scale thermodynamics? Usually when we think of thermodynamics, we think of Avogadro's number of particles. To introduce these ideas, I'm going to introduce some thought experiments that by now we're used to, Ziller's engine and Landauer's principle. Ziller's engine is a device for obtaining work from information. Suppose you have one bit. You have a particle in a box. You know that the particle is in the box's left-hand side. You can slide a partition into the box, tie to the partition a rope, and tie to the rope a weight. Suppose that the particle is coupled through the box's walls to some temperature T heat bath. We can model the particle as an ideal gas. It's going to expand. It's going to push the partition to the other side of the box. At that point, you've lost your information. You don't know where in the box the particle is, but you've lifted the weight. You've traded information for work. We can reverse this process, start off with a particle that's anywhere in the box. We can slide the partition halfway through the box. We obtain information about the particle's location, but because we are compressing an ideal gas, we had to spend work. These thought experiments illustrate what I'm calling the big idea, which is written in big font because it is a big idea. There is an interplay between information and energy on small scales. Now, how about those small scales? What's the motivation for considering them? There are some contexts, experimental contexts, in which the language of information and the language of thermodynamics are used, but when we're talking about single molecules, there are people manipulating single molecules. For instance, this picture is a picture of a DNA hairpin, just a loop of DNA. The legs are pulled apart and released so they come back together. This was done a few years ago to illustrate Crookes' theorem, a result in statistical mechanics. During just classical computation, because transistors are quite small, heat removal can be a problem. And of course, in quantum computation, we're very concerned about heat because we're concerned about decoherence. In all these contexts, we might want to consider the interplay between information and energy on small scales. I'd like to make these ideas more rigorous by introducing the resource theory framework. It's a tool in quantum information theory, but I'll talk about what it is and focus on three sets of resource theories. One is the resource theory of non-uniformity, which is a resource theory for information, for bits, for particles and boxes. This generalizes to few sets of thermodynamic resource theories. One family is what I call the Helmholtz resource theories. These have been studied a great deal. They model exchanges of energy between systems and heat baths. But there are many other types of baths, many other types of interactions, so the whole family of those is the resource theories of non-equilibrium. How do we address these theories mathematically, and what results do we get from them? I'm going to use Lorentz curves and single-shot entropies. These are alternatives to the Gibbs entropy, the Shannon entropy, and the von Neumann entropy that we've been hearing about a great deal. The results include answers to our questions, how much we can get from states, and how much energy or free energy or information we need to invest to create a state. This picture is meant to illustrate we all have some idea of what a resource is. It's just something that's useful. And in different contexts, different things are useful. Probably the most famous example of a resource theory is that of pure bipartite entanglement, which has a lot of syllables, so I'm just going to call it entanglement theory. When we use a resource theory, we have in mind an agent, some experimenter who has certain tools, materials, and skills. The experimenter creates and manipulates quantum states. When we talk about resource theories, we talk about transitions from state rho to a state sigma. What can turn into what cannot turn into what, how much of this can turn into how much of that. As Chiara said, what is impossible and what is possible. Each each resource has three interrelated defining characteristics: free states, resource states, and free operations. We're going to use these to characterize our resource theories of interest. I'm going to do that using this chart I wrote on Rob's Beckons. In this column, we're going to state our characteristics. Here, we're going to list the resource theories of interest, and here we're going to characterize the resource theories of interest. Here's some background about the thermodynamic resource theories. The Helmholtz resource theories, as I said, have been studied for a number of years by a number of authors. They're also called resource theories of athermality. Sometimes they're also called just the thermodynamic resource theories, though there's a bit more to thermodynamics than the Helmholtz theories. The results do relate to the Helmholtz free energy in a way that I can talk about a bit later. Again, these theories model interactions between systems and heat baths. Suppose you start off with this theory and set all the Hamiltonians to 0, so that they're totally degenerate. They're trivial, you can ignore them. The result is the resource theory of non-uniformity, which again is a resource theory for just information. It was first talked about in 2003 by assorted Horodetsky's and a few others, although they didn't use the name non-uniformity. The resource theory of non-uniformity is useful for two reasons. One, it's interesting in its own right, because it is a resource theory for information. And two, it's this simple example of a thermodynamic theory that can help us understand the more general theory. I like to make a comparison to a problem of spin subject to a bunch of magnetic fields. The dynamics in that system are very complicated. In order to really understand what's going on, because some of us are physicists, we might want to start by simplifying the problem, setting the fields to 0. We can build up tools and intuitions, and then put in the complications. Setting the fields to 0 in the spin problem is like setting the Hamiltonians to 0 in thermodynamics. It's another reason why the non-uniformity theory is useful. These people studied the asymptotic version of the theory. What do I mean by that? I said that in resource theories we study transitions. Consider transition from n copies of the state rho to n sub n copies of the state sigma. Now consider the limit as n approaches infinity. This is the asymptotic regime, sort of the thermodynamic limits. But we usually don't have n approaches infinity copies of anything. That's why it's worthwhile to consider the single shot limit, just single copies of states. This was treated in 2013. It's a generalization that et al. Includes younger Halpern.
Sorry, Nicole, what is the contrast between the two halves of this slide?
What's the difference
what
between
are you saying about the
these and these?
Yeah.
In these, we consider Hamiltonians. People tend to define whatever Hamiltonians they like. So all sorts of Hamiltonians are considered in that theory. Whereas in this theory, the only Hamiltonians that are considered are ones that are totally degenerate. You could think of all the eigenvalues as being 0. So you don't even have to talk about Hamiltonians. Here, if you wanted to define a state, then you specify a Hamiltonian and a density operator over the Hamiltonian's levels. And here, you just have to specify the density operator to specify a state, because all the levels are degenerate. So again, this is a simple limit of this, in which all the Hamiltonians are 0. Again, there are so many types of baths. There are heat baths, there are heat and particle baths, there are heat and volume baths. There are so many types of interactions, and there are so many different thermodynamic potentials. That's why we might want to consider an entire family of resource theories of non-equilibrium that include these and this, and a few others that relate to the Gibbs free energy and so on. That's something I'm working on currently, but for time's sake, I won't say much more about them here. What are those defining characteristics? Because of the tools and materials available, the agent can create as many copies of certain states as he or she wants, basically at 0 cost. In this approximation, at 0 cost. In the entanglement theory, the free states are product states because the tools and materials around are classical. In the Helmholtz theories, these are canonical ensembles. I keep saying Helmholtz theories because there is one temperature associated with each Helmholtz theory. We think of the agent in one Helmholtz theory as having access to a giant heat bath at some temperature. That temperature defines that Helmholtz theory. The agent can create for free, draw from the heat bath, any canonical ensemble relative to that special temperature and any Hamiltonian. This is where the Hamiltonians come in. Now, suppose that you start off with this state and set the Hamiltonian to 0. The result is a maximally mixed state, or a uniform state, which is free, in the non-uniformity theory. To specify a state in the non-uniformity theory, you just have to specify the dimension of the space on which the state is defined, and the spectrum. So sometimes I'll say spectrum, sometimes I'll say state, and sometimes I'll say probability distribution. When I'm talking about the non-uniformity theory, these are the same, because the quantum version of the theory reduces to the classical version. Let's fill in first our example resource theories and their first characteristics. Product states, canonical ensembles, and uniform distributions are free. Any state that is not free is a resource. The agent cannot create it for free, but maybe a friend in the lab down the hall can create a copy of such a state and loan it to our agent. In the entanglement theory, entangled states are resources. For example, this bell pair is especially valuable. We can use it to simulate a quantum channel. In Helmholtz theories, just any athermal states, any states that are not Gibbs states relative to that special temperature, are resources. In the non-uniformity theory, all non-uniform states are valuable. In particular, the pure state is especially valuable. Again, I want to illustrate that the non-uniformity theory does model information, locations of particles in boxes. This state models a particle in a known one of 4 compartments if the compartments have equal sizes. Let's fill in the next row of our chart. Resource states are entangled, athermal, or non-uniform. Finally, free operations. Because of the tools and materials available, the agent can perform certain operations at 0 cost. In the entanglement theory, these are local operations in classical communications. In the Helmholtz theories, they're called thermal operations. They tend to bring states toward the associated Gibbs states. Each thermal operation consists of up to 3 steps. It looks a little horrible, but we can work through it. Suppose you start off with a state rho, and you're about to transform it by a thermal operation. First, you can tensor on any canonical ensemble relative to that special temperature. Then you can transform by any unitary. That preserves the total Hamiltonian. The total Hamiltonian is just the Hamiltonian associated with your state rho, plus the Hamiltonian associated with the state that you just tensored on. So this is an implementation of energy conservation. Finally, you can throw away any subsystem associated with its own Hamiltonian. Now suppose we start with this definition and once again, set the Hamiltonians to 0. The result is a set of noisy operations. These are free in the non-uniformity theory. They tend to map states toward the uniform states because when information is valuable, it's all too easy to introduce noise. But if you have a state rho to begin with, you can tensor on any maximally mixed states, transform by any unitary, because the Hamiltonians are 0, every unitary is going to preserve the total Hamiltonian, and you can throw out any subsystem. Let us fill in the final row of our chart. Free operations includes LOCC, thermal operations, and noisy operations. Now that we've characterized some resource theories, let's see how to deal with them mathematically. We're going to talk about Lorentz curves, single-shot entropies, and cost of creation and distillable resourcefulness. I'm going to focus on the non-uniformity theory, but these results generalize to the other thermodynamic resource theories. A Lorentz curve is a visualization of a probability distribution. It was discovered, I think, in the 1920s in economics, used to illustrate how unevenly wealth was distributed amongst a population. Unevenly is the same thing as non-uniformly, which is why we're using these in the non-uniformity theory. Let's see how to draw a Lorentz curve. Here's an example probability distribution or spectrum. We order it from greatest value to least value. Each Lorentz curve stretches from 0, 0 to 1, 1. We divide up the x-axis so that there is one place per value in our probability distribution. We divide up the x-axis evenly, and each of these locations is associated with one point. Apart from the origin, the first point has a y-coordinate that is the greatest value. To get the y-coordinate of the second point, we add the second greatest value. As we move along the curve, we keep adding values. Then we connect all the points with straight lines, and voila, here's our Lorentz curve. Note that it is concave. It bows away from the x-axis, or at worst, it stretches straight from 0, 0 to 1, 1. That illustrates any free state, any worthless state. So the more that a curve deviates from this straight line, the more resourcefulness the state encodes. For example, here's an illustration of a pure state. Remember, pure states are quite valuable. So this curve is quite different from that straight line. The Lorentz curve has an interesting anatomy. I'm going to focus on two pieces of them, two pieces of the Lorentz curve, and thereby introduce the single-shot entropies. This first part of the curve that starts at 0, 0, I call the on-ramp, like on-ramp to the highway. It has a slope that's easy to calculate. Slope equals a rise over a run. In this case, the rise is our greatest value, which I'm going to call P max, and the run is 1 over the dimension of the space. I'm going to move the d into the numerator, then simultaneously exponentiate and take logs. I can use a log to change this to a minus sign while putting P max in the denominator. Does anyone recognize this quantity?
Surprisal.
Sorry?
Surprisal.
It's a ready entropy. Sometimes called H max.
That's right.
It's the ready infinity entropy. Let me put that on the slide. That argument is a very important quantity, so we call it I infinity for a reason I'll state soon. This is a monotone under noisy operations. Suppose you start with the state rho. You can draw its Lorentz curve. Then you transform rho by noisy operations. This quantity either stays the same or decreases. So this on-ramp either stays the same or moves downward, because noisy operations map states toward the uniform state, and that has the lowest possible on-ramp. We call this I for information measure, because it is something that decreases under noisy operations. It's distinct from another important information measure. That characterizes what I call the tail. The tail is its final flat part of the Lorentz curve. And it has the following length, which looks a little funny. This is the expression for the length of the tail. It involves this other entropy, the Rennie's zero entropy, H0. It has this definition. It's just the log of the number of non-zero eigenvalues of rho. Why should the tail have this length? Well, note that we form the tail by adding zero-valued eigenvalues to the y-coordinate. So everything that is not the tail corresponds to the non-zero eigenvalues. The number of non-zero eigenvalues is given by H0. The entire Lorentz curve has this horizontal length of 1. Let's subtract off the length of the non-tail part of the curve, which again corresponds to the number of non-zero eigenvalues, H0, times a length scaling factor 1 over d. That's how we get a log d here. We have the length of the entire curve minus the length of the non-tail part equals the length of the tail part. Again, this argument is very important. It too is a monotone. We call it I0. So in the language that you introduced, we would call this relative entropy, and the other is a relative entropy as well. It's a single-shot relative entropy between the state rho and the maximally mixed state on the same space. As we process rho by noisy operations, the tail either stays the same length or shrinks, because the uniform state has the smallest possible tail. It has length 0. To illustrate what we just saw, note that the pure state, which is very valuable, has a very steep on-ramp and a very long tail, unlike the uniform state. Clearly, Lorentz curves have something non-uniformity theory, but how exactly do we use them in the non-uniformity theory? We use this handy-dandy theorem. It says, suppose you have a state rho, and you're wondering whether it can turn into a state sigma by free operations. The Lorentz curve for rho remains above or on the Lorentz curve for sigma if and only if noisy operations can transform rho into sigma. Let's illustrate that. Here, the Lorentz curve for rho is everywhere above or on the Lorentz curve for sigma, so noisy operations can transform rho into sigma. So when you see that no, think, yes, noisy operations can make the transformation happen. In contrast, in this picture, the rho curve dips below the sigma curve, so rho cannot turn into sigma. How do we generalize to other thermodynamic resource theories? We rescale. This is a picture from a paper by Nicole and Jonathan Oppenheim. It looks a great deal like our Lorentz curve. But note that the x-axis is not divided evenly. It's divided into Boltzmann factors. Why Boltzmann factors? We've been using Lorentz curve to illustrate spectra, which encode just information. But as we talked about at the beginning of the presentation, information and energy, specifically free energy, are both resources and can be interchangeable. So we would like to incorporate free energy into our Lorentz curve so that the Lorentz curve represents the entire value of a state. So we've already incorporated the spectra, the information contents of the states. We incorporate the free energy content by rescaling by Boltzmann factors. This is a summary of what we just saw. By the way, I'm not going to have the time to show exactly how we use Lorentz curves, but they do simplify proofs and offer some nice intuitions. Now, let's return to the questions we asked at the beginning of the session. And let's tweak them one last time, make them a little more quantitative. Instead of asking just what can we get from information, let's ask how much information we can extract from a state rho. We call this the distillable non-uniformity. Or in one of these other thermodynamic resources, it would be the distillable sort of free energy or non-equilibrium mix. We can also ask how much information in some standard state would we need to create the state rho. We're familiar with these two questions and two concepts from two other contexts. One is the entanglement theory. There is distillable entanglement. This is the number of bell pairs that you can extract per copy of the state rho. And there's also the entanglement cost of creation, the number of bell pairs that you would need to form some state rho. The other context is good old-fashioned thermodynamics. Or what I like to call the appearing rabbit story. I got this story from textbook. I think Ian knows about it. You are a magician. You're about to pull a rabbit out of a hat. Because you are also a thinking person, you want to calculate exactly how much work you perform when you create the rabbit from scratch. If you just want to create the rabbit, then the amount of energy, on average, that you need to invest is just the internal energy of the rabbit associated with its atoms, its molecules, maybe modulo some potential. Suppose that you also want to warm up the rabbit to room temperature. The amount of work you have to invest on average is the Helmholtz free energy. In different contexts and different tasks are associated with different thermodynamic potentials. Note that in this thermodynamic limit, the asymptotic limit, the distillable free energy equals the energy cost of creation. So if you annihilate your rabbits, then the amount of work you can recover is the same as the amount of work you had to invest to create the rabbit. However, that's on average. In the single shot regime, if we're talking about just one rabbit, then you can usually get out less than you had to invest. It's the second law, you can't win. So let's see some particulars. First, the non-uniformity cost of formation. Suppose I'm interested in the minimum amount of information, non-uniformity, in some standard state, sort of like a number of bits, but a generalization, similar to a number of bell pairs, that you would need to create a state rho. We represent rho by this solid Lorentz curve, and the standard state of information that has just become easy to use, like dollars, like bell pairs, is represented by a curve that's entirely tail and on-ramp. Well, the minimum lowest possible curve follows the on-ramp of rho, and then the rest of it is tail. Its key characteristic is having the same on-ramp slope. The on-ramp slope is given by h infinity. That's why we quantify the minimum cost by I infinity. I infinity differs from I0. Remember, I0 is defined in terms of H0. This quantifies the non-uniformity distillable from just one copy of the state. Again, the bold curve represents our state rho. This dashed curve represents the maximum possible distillable amount of information. According to our theorem, because the bold curve is everywhere above or on the dashed curve, noisy operations can transform rho into this I0 curve, and so the I0 curve is distillable. That amount of information is distillable. Once again, these two entropies differ from each other. So in the single shot limits, in general, the distillable information, free energy or resourcefulness, differs from the resourcefulness cost of formation. In contrast, in the thermodynamic limit, on average, the two quantities equal each other. But what's nice is from these single shot results, you can recover the thermodynamic limit. In summary, we've talked about resource theories, what they are, how they can be useful. We focused on three families of resource theories. One, the resource theory of non-uniformity, which is interesting for two reasons, because it's a resource theory of information, and also because it helps us understand more general thermodynamic resource theories. The Helmholtz resource theories model interactions with heat baths, and in general, resource theories of non-equilibrium model thermodynamic exchanges. We represented these resource theories using Lorentz curves and single-shot entropies. We also saw that in single-shot limits, cost of creation and distillable resourcefulness can differ, even though they're the same in the thermodynamic limit. That's just one of the results that comes out of these resource theories. Again, if you remember anything about this talk 6 months from now, apart from the cute rabbit picture, let it be the big idea. There is an interplay between energy and information on small scales. Now is when experimenters are dealing with very small scales. Now is when we have the quantum information tools. Why not put them together?